Hi, this is Bill Foote. This is Stats 1, and we kind of take a breather with Lecture 7. We're calling it Practice Makes Progress. We're still following the pose, form, sample, count, and infer workflow. What you see here are three questions that might come up in, I don't know, if somebody were to evaluate how far we've come. They're all going to be based on the Gaussian model. The same things could be used for the same questions could be applied to a Poisson or binomial model just as easily. But the Gaussian model has two parameters. There's a mean and a standard deviation that we're solving for inside of this. And the first question that we would pose is, just how plausible is it to achieve a grade point average greater than 2.8? So that's the first one. So that's a probability question. And we could also answer that question in terms of odds, should we decide ever to do that, following what we did in Lecture 2. Second question we can ask that follows right on the first is, what grade point average can I expect that's better than 2.8? So they're very much related to one another, but there's a extra transformation that has to go on into to answer that question. Finally, or maybe we should have started with this, are there any outliers? So we have some data here. Just open this up a little bit to see how we formed several hypotheses, 22 in this particular case, 11 mu's or means, and just 2 sigmas, and a probability of each equally at this point. And then as we add data, the final result will keep changing and keep squeezing in, like we said, concentrating, pulling away from tails from maximum and minimum of the data, and kind of moving in and pinching in toward the mean. Here are 8 grade point averages. We said, grade point averages are just pretty much the same thing as any performance indicator. So these would be 8 performance periods. That would be the data. And each and every one of these is a probability. So we multiply all the probabilities together, which means we're multiplying all this one, all of these, into a joint probability, which, we need to expand these zeros. In production work, this is usually done with logarithms. But for our purposes here, we're going to be fine. And really, the point of this is we have 22 different likelihoods here. And what we're going to do is, and these are all joint probabilities, in the sense that we are looking at the probability of a particular hypothesis, like a mu of 1 and a sigma of 0.5, which might occur 5% of the time, across the probabilities of seeing each and every single one of these data. And that's all both and the probability rule for both and, of course, is multiplication. Until we get this multiplication all the way out, we sum all 22 up, and we have this lovely piece right here. And that allows us to look at the relative sizes of each one of these, and that's the important piece. Now the thing is, what we get is 2 of them. Got to keep remembering that. 1 for each environment. So what that means for inference, so we've done all our counting here, these probability of a hypothesis given all of the data. We have 22 of them. We can put them side by side like this. We've already done all of this. Here are the 11 points from 1 to 4 of a grid approximation on the left, 2 sigmas, and we're just putting those 2 pieces side by side. Again, in production work, we'd use an index and match to perform this spreading out the stacked data that those probabilities of hypotheses given data are. That's the stack. Now, we would then calculate the probability of each and every mu, and of course the probability of each sigma. In this case, it's basically a high volatility environment. That's what bottom indicates. And each one of these calculations, I will take one that's a little bit more meaningful about this one. 1121 is done by adding the probability of seeing a mu .2 in this case, given that sigma is 0.5, and we add to that mutually exclusive probability of the mutually exclusive mu equals 2.2 given a sigma equals 1.0. That's because they are mutually exclusive, completely exhaustive in this row. So we add the probabilities together. Completely exhaustive is going to come up when we add the whole thing all up, because it will add up to 100%. And that's where we're getting the 0.0039. We're adding to that 1082. Okay, so far, it's just a review of what we've been doing up to this point, but it's a good reminder of how this works. And one more thing that I put here is the cumulative. So the cumulative is what's the probability of a mu less than some number? What is the probability of a mu less than 1? Nearly 0. That's what this first one is. And then we take that and add to it the increment, the 0.0001. Take that and add to that the increment in the next mu, 0.0026, and so on all the way down. These should, of course, add up to 1. It should accumulate to 1. This is the infamous ogive. Well, whatever it is, can we answer that very first question? What was that first question? There we go. Just how plausible is it to achieve a GPA greater than 2.8? That was the first question. Where is the... Now, let's get rid of that. Funny business out. There we go. Okay. What is where greater than 2.8? Okay. So we're looking for the probability. Go back to green here. The probability that a GPA, the mean, is greater than 2.8. Now we're dealing with all means here. It's the mean of a GPA. Okay. What is the probability that it's greater than 2.8? So we're really only going to look here at this subspace of all of the mu's. So we're looking at 3.1, 3.4, 3.7, and 4.0. And it's possible that we could, if we were looking for a specific one greater than, say, 2.81, we could do some interpolation between the probabilities of 0.3625 and 0.1375 between here and the lamppost way down the street. It's not going to matter so much. So we're going to take the easy way out and simply compute all of these probabilities. Well, that's fairly easy to do if you've already done this job of doing the cumulative probability. That should be equal to 1 minus 0. And take out all of these, which is equal to all of these. The 0.8256 is equal to the sum of 0, 1, 26, 242, the 1121, the 3241, and the 3625. And if we perform this exercise, we should be getting, let's see, a number like 1754. So 1754 plus 8256 will add up to 1. BC, the completely exhausted. That's one way to do it. The other way to do it is just to add all of those up. And if you do add all of those up, 13, I'm just doing it ahead here. 0, carry the 2, 0, carry that. Yeah, that's 1754 as well. So you can do it either way and answer the question. But the reason why all of this works is BC. CE part is here, 1 minus. The ME part is adding mutually exclusive 1375, 326, or adding up 1118 plus 2507 to get 3625, if you can find it here at 2.01. So we got the first one answered. About the second one, what GPA can I expect better than 2.8? Well, that's the follow-on question. What GPA in this range is the expected value? Now, the way we do that one is we take the outcomes through 0.1, 0.4, 0.7, oops, and 4.0. Those are our outcomes. And we're going to multiply these times probabilities. We're going to weight them. Then we're going to sum them all up, and we will have our answer. But what are the probabilities? Well, they're not these, because those are improper. They don't add up to 1. They're relatively sized correctly. But just like we did, oh gosh, up here, where we have the same situation, we have 22 of them, and we had to add them up and take each one of these and divide it by 1.4 times 10 to the minus 5th power, all the way down through to get these probabilities. Now, all of these will add up to 1. Same idea. Well, these certainly will. In fact, they seem to add up to what? 17, I think it's 1744, not 7. Arithmetic. Oh, we can do higher math, not arithmetic. 44. These add up to 1744. Caught that mistake, terrific. Well, we take 13, 75 and divide it by 1744 to find its probability. Go to 6 divided by 4, 0.0040 divided by the same thing again and again and again. And finally, 0.00002 divided by 17. Okay. up here. It's right next to it. Okay, good. Now it turns out that this is the same. If we perform this, I think I've got the numbers already worked out. 75, 19, 2, and a little bit more. This probability is 75%. This one is 19%, and this one is very small, 0.2, just 0.2%. This one is really small, 0.001. Multiply all these together and get our weighted average. We should get 3.1711. So we have the answer to the second question. But the reason why we do this is a process called normalization. Again, almost probabilities here, joint probabilities, they don't add up to 1. So we normalize them so they do add up to 1. Their relative position is still going to be the same. The ratio, they're going to be exactly the same, which is why the procedure of normalization works. But they now add up to 1. So now we're always going to get a number between 3 and 4. If you do not do that, guaranteed you will not get a number between 3 and 4. You'll get a number around 2, 8, 2, 7. That's the required reason. That one. And are there any outliers? Well, let's see. Here's our data up here. There we go. And let's see if we can play with this a little bit. So here's our data. The first thing we do in using, and we're going to use cookies analysis here, we're going to build on this. There's 5 ways. It's a whole lot more than that, but there are 5 ways that we're going to look at in this course to examine outliers, things that are not within what we're going to call the body of the distribution. And we're going to say that because they don't behave the same way as the main parts of this distribution. And remember, this distribution looks like this. Let's see if we can do that. And these tails probably have a life of their own, where this distribution looks very suspiciously quadratic. You gotta remember, we did see a quadratic once in lecture 1. Yes, we did. Yes, we did. We added a single piece of data and then another piece of data, and we all of a sudden the distribution became quadratic. And as we added more and more data, this is on the binomial, as we added more and more data, we created tails. The quadratic started to spread out like this. Amazing buildup and an amazing regularity. Right now, let me just, I don't want to do that either. Let me just get rid of this so that we can operate on these 8 numbers. And we can get rid of those. Okay, a little bit easier to see. The first thing we do is we're going to put them in order. The first one is going to be we want 1, 2, 3, 4. And we know the middle is going to be right here in this rank order, and these are rank order statistics that we're going to be coming up with. And we have the middle of this on that, okay? And we're just going to take the averages. Now, this is fancier ways of doing this, interpolations that are not simple averages. They're weighted averages, actually. Back to that. But we're going to keep this simple because we want to create, in this particular case, a back of the envelope approach, something that can be programmed. Let's put this in blue. So I think the lowest one is what, 1.75. Yeah. Highest one, I think, is 3.75. Very similar to the old bubble sort. We bracket it. So we've gotten rid of this one. We gotten rid of this one. The lowest one now is what? 2. And the next highest, the highest one now, and it's literally the lowest one now, the highest one of what's left. Should be 3, 6. And now we look for the lowest one of what's left. And we should get 2.1 here. And the max of what was left should be 3.1. Nice little algorithm brewing here. And the next one should be easy, 2.9, 2.2. So we're doing this bracketing sort, similar to a bubble sort. Bubble sort's even more complicated. Of course, everything's more complicated. So the median, which we're going to call Q2, is the 50th percentile. 50% of all the data is above. There's 4 items. That's 50% of the data. And 50% of the data, 4 items out of 8, is below this number. And somewhere on average between 2.2 and 2.9. Now, the average ends up being 2.55. That simple. And we also pick up literally the median of what's below the median and the median of what's above the median. Okay, all about medians now. And this is a lovely system because with even numbers of data, it's going to be the same thing all the way across. If you had 100 items, you go between the 49th and the 50th, right? 50 above, 50 below. 50, oh, 50, 51. Okay, yeah, okay. Rank order. And then you split the 50 above. Okay, and you keep splitting. It's exactly the same idea. This is called Q1. It's the 25th percentile because 25% of all the data, which is 2 out of 8, 25% is below this number. And this number is 2.05. And 75% is below this number up here, which is called Q3. And the average of 3.1 and 3.6, let's put that 5 to 3.35. That. Okay, so we have almost everything we need. The difference between the 25th and the 75th is called the interquartile range, because we have quartiles. And that's 335 minus 205, or 1.30. And always remember, the units of this are in grade point averages. Okay, it's a grade point. That's the unit. Okay, IQR. And John Tukey says, take the 335 and add to it 1.5 times the IQR. By the way, that ends up being 1.95. And in the other direction, subtract 1.5 times the IQR. And when you do that, we create two, a lower and an upper fence. For the lower fence, I'll just write it over here more distinctly. L equals for lower Q1 minus 1.5 IQR, 2.05 minus 1.95, or 0.1. So you have to have a grade point average of 0.1, less than 0.1, right on 0, in order to say you have an outlier. Now, we're all scientists regarding our own performance, so we're just going to say, no, that's nonsense. This is a low. And by the way, this is high. We're going to say those are outliers, and that would be quite reasonable too. But using these formulae, you got to believe the 1.5. You got to believe that you're subtracting or adding 1.5 times the IQR. Okay, so you got to think that it's above and below the 75 and the 25, and that's reasonable for an outlier. In the upper direction, we have Q3 plus 1.5 IQR, 3.35 plus 1.95 gives us a whopping 5.3, but check my math. And of course, we only are allowed to go up to 4. Okay, so we have some bounds here on the scale that the Tukey mechanism does not obey. So that would be the result. That would be the answer. We have no outliers. Why? Because it's off the scale as we have defined it for the fences. The max is less than the upper. The min is greater than the lower as predicted by Tukey. So he'd say this would be fine. Actually, probably wouldn't. He'd say, let's look at some other way to do this. And we're going to look at 4 other ways. Chebyshev, can't wait to see that. And just looking at the tails of our distribution down here. We have mu's that, 0 probability at 1, near 0 at 1.3. We get somewhere between, our 175 would be here. Our 175 would be between 0.6 and 0.9. So that's pretty low probability. 2.69% is the probability of seeing something around that region. Same in the other direction. We might use that as an indicator of outliers. Not today, not in lecture 7. We're just practicing what we have learned up to this point with a parameter, multiple hypothesis approach that employed normalization, that employed mutually exclusive, completely exhaustive rules, multiplications, No, we didn't do any multiplication of probabilities here. We did all additions of probabilities to get our results, but realizing that the multiplications have already happened, both and statements. And that mutually exclusive means either or. With all those lovely thoughts, as we make our way on to the next phase of our study, where we're going to do some simulation. It's going to be very interesting. I'm going to carry this forward, produce a forecasting model, actually, with all this probability we've been doing. I'll leave you with that. And again, thank you very much for your kind attention.